Okay, so we are now on page 70. We're going to talk about the linear correlation coefficient, which is the R value. Okay, so we already know how to calculate it. We know what it is. It describes what? Top of page 70. It says the linear correlation coefficient is denoted by R, and it measures the strength of the linear association. How strong it is. Okay. R values can be between what and what? We talked about this yesterday. -1 to +1. The closer you are to 1, the stronger the correlation is, right? So, blah, blah, blah. Example number 4, quickly read that. Consider data table 210, blah, blah, blah. Okay, so yeah, the book uses what is called a stat disk. It's another, their own proprietary statistical modeling thing, okay? If you're interested in, please go and take a look at it. It does the same thing for you just as your calculator did, right? If you look at the stat disk, it gives you the sample size, degrees of freedom, we'll talk about that later, then the correlation coefficient, right? And then it gives you the critical value, critical R, and then it gives you the p-value, all these other things. Okay, so, and go to page 71. I already told you about that table. You do not have to memorize this table, okay? If you need it on a test, I will give it to you. Okay, but know how to use it, okay? Why is it that the less numbers of data, the required R value becomes higher and higher to call it a linear relationship? Because that's what you're showing, right? The more data points you have, the less value of R you can still call to be a linear relationship. Why is that? Let's go back to the one that we just had here, right? The less data that I take means that the less likely I will get the 79,790 outlier. Does that make sense? Okay, so therefore it requires to be a much closer relationship. Okay, in other words, less likely, the less data that I have, less likely I'm going to get an oddball that's going to throw me off, right? And therefore, the R value looks like that. If you look at on the right-hand side of the figure 2-17, there's a simple diagram there. Make sure you understand that. Make sure you understand that the negative values are just as same as the positive values. It's just a matter of whether it's a negative linear or it's a positive linear, right? Okay. P-values. So on the bottom of page 71, there is a thing called a p-value. Anna, read that for us.
Sorry, in the yellow box or the...
Yeah.
Okay, sorry. If there really is no linear correlation between two variables, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data.
So you all understood that, right? Pretty simple stuff? I don't think so. Right? If you understood this, you're way ahead of the game. Okay, there's no way you understand what this is. Okay, don't worry about it. Okay, understand there's a thing called p-value. Flip the page. Flip the page. Now, on the top there is a paragraph in bold. Now let's read this one. Maybe this one will make sense to you. Only a small p-value, such as 0.05 or less. Oh, here we come again, that 5%. Remember we talked about that 5%? What was statistically significant? Right? That 5%. This is coming back again, okay? So only a small p-value, such as 0.05 or less, suggests that the sample results are not likely to occur by chance when there is no correlation. So, a small p-value supports a conclusion that there is a linear correlation between the two variables. So, when you see a p-value, what are you looking for? Looking for a p-value that is
5%.
less than 5%, right? If it's less than 5%, that means that linear correlation. That's all you're looking for, okay? So this does what? It takes away the need for the looking at that, how many data points do I have, right? Do I need a certain R value, right? This does this for you. Okay, so this will actually, because the p-value is dependent on how many data points you have, okay? So you'll just calculate a p-value and you will say, is it greater than 5% or is it less? If it's less than 5%, I can say that it is a linear relationship, okay? And that's the value of the p-value, okay? Example number 5. Correlation between shoe print lengths and heights. Welcome back, Spencer. Go ahead and read it for us.
Example 4 used only 5 pairs of data from data set 2, foot and height, and appendix B. If we use the shoe print lengths and the heights from all of the 40 subjects listed in data set 2, appendix B, we get the scatter plot shown in figure 218, and we get the mini tab results shown in the accompanying display. The scatter plot does show a distinct pattern instead of having points scattered about willy-nilly. Also, we see that the value of the linear correlation coefficient is R equals 0.813, and the p-value is 0 when rounded to 3 decimal places. Because the p-value of 0 is small, we have sufficient evidence to conclude that there is a linear correlation between shoe print lengths and heights.
Thanks. All right. So great. So as you can see there, now there's another relation. There's another scatter plot there. If I were to describe the scatter plot, what would I be able to say, Evan?
Positive.
Positive.
The shoe print length goes up, the height goes up.
Okay, that's good. What else?
Linear.
It's linear. Okay.
This is
And how can I say that's? Why can I say that's linear?
the P is under
Because the
5%.
p-value is less than 5%, right? So it is definitely a linear. It's positive. I don't see any huge outliers, right? Okay. Are we good? Everybody understand that?
How do you get the p-value? Is it on your calculator?
It's on your calculator.
Oh, okay.
You will later on calculate. So, like on the quiz that we're going to say, I will not ask you to calculate the p-value. I will give you the p-value, and you just have to interpret it.
Okay.
Okay? All right? In second semester, definitely you will be calculating your own p-values. Okay, that'll be a huge thing, but not until we learn everything going up to that point. Okay, so this is kind of a preview for you. All right? Okay. All right, we're done for the day. We are done for the day.